All right, so here's the definition or definite integral, section 5.4, definite integration and fundamental theorem of calculus. So real quick recap, because I think I did this in 5.3 for an unknown reason. Quick recap, what is the fundamental theorem of calculus? The fundamental theorem of calculus says if f is continuous on AB, then we usually start off our equations like that. Here's what the fundamental theorem of calculus says. The integral from a to b of f of x dx equals the antiderivative, see why that's why it's a capital F, at b minus the antiderivative at a. So this is anti at b, and this is anti at a. Okay, so basically the picture of this is you could have any crazy graph, f of x, right? That's f of x, and I wanted to find the area under the curve, because that's what definite integration stands for, between the line x equals a and x equals b. So if I wanted to find this crazy area here, so there's no geometry formula for that, then I just need f of b, which takes the area from here all the way back, minus f of a, which takes the area from here all the way back. So it's like you're taking the whole area, this capital F of b finds the area between your curve and the x-axis and the y-axis. And then you're removing off f of a, which finds the area between the curve. It kind of changed it a different color. You're chopping off the part you don't want. And you're left with just that purple, which is cool. Okay, so that's the fundamental theorem of calculus. Now what it usually is written at before this is capital F of x evaluated from a to b. So you have to know how to say these things. That's what you could squeeze in right there. Anyway, let's do some examples. It's a lot like our regular derivatives, but you have an extra step at the end, and you don't have plus c's, so I like it. Alright, so first of all, to pronounce this, I'd say the integral from 1 to 5 of x squared dx. So I want to take the integral from 1 to 5. So first thing you do is take the antiderivative, which is our rule. You take the old exponent and you raise it up 1. Do that first, and then divide by the new exponent. And I put it in brackets, and I put a 1 and a 5 there to indicate that I am not done with this problem yet. You have to plug in the endpoint first, kind of like how we did in the picture. So you're going to plug in the 5 first, 5 cubed over 3, and then subtract off the part you don't want, which is 1 cubed over 3. So if you do that, 5 cubed over 3 is 125 thirds, minus 1/3 is 124 thirds, which is 41 1/3. I kind of like turning them to mixed numbers because it gives me an idea of the area. So if you thought about it, you know what x squared looks like, right? It looks like this. Okay, well if I took the area from 1 to 5, imagine that crazy shape. It would be like this. Right? It's kind of like a triangle, but it's curvier. The area of that crazy triangle is going to be 41 1/3 units squared. Cool. That's what we find. So let's do a couple more. I know I did this one kind of like this one the other day. Let's say from 3 to 8 of a constant. Let's say 4 dv. One thing that could catch people is here you see their x's, so you know they're still x's. This letter actually tells me my variable, and this one's v's. So if I make the exponent go up 1, it's 4v, evaluated from 3 to 8. So you're going to plug in the 8 first, 4 times 8, minus 4 times 3. Okay, and we got 32 minus 12 is going to be 20. 20 square units. If I graph that, 1, 2, 3, 4, this is a horizontal line at 4, and I'm only keeping the chunk from 3 to 8. So here's 3 to 8. It's a rectangle. I could just say it's 5 times 4, and that confirms my 20. You don't really have to draw the picture every time, but I like to go back to the picture just for sake of memory. So then you can get crazier ones like this. Let's go with 3x squared plus x minus 2. So I like these problems. They're pretty easy. They get more complicated when you have more than one term, because it's really easy to plug in here. But these can get a little trickier. So here, I'm going to take the old power, raise it up 1, divide by the new exponent. That's going to cancel nicely. Then I take the old power, raise it up 1, divide by the new exponent. And then last one, raise it up by a power. You don't need a plus c in this one because you're actually plugging in numbers, finding the area under the curve. Alright, so maybe I'll clean this up a little bit before breaking it into its plug-in parts. So that's going to be x cubed plus 1/2 x squared minus 2x. Now you're going to plug a 3 into every piece, and then you're going to plug a 0 into every piece. So it's a good idea to leave yourself space. Make sure you do it one at a time. Take your time on this step. And I recommend using parentheses. It doesn't make a difference right now, but if you ever get a negative in here and you don't use parentheses, you're going to get it wrong. Alright, so you're going to put a 3, 3, 3, and here you're going to put a 0 and 0 and 0. Now after you do this once or twice, you'll really just put a 0 in for that, because everything has an x on it, so everything's being multiplied by 0. So the front part, you got 27, half of 9 is 4.5, minus 6, it's going to be 25.5, minus 0. If you graphed it, you'd see some sort of parabola from 0 to 3, and the area is 25.5. Alright, let's do a weird one now. Okay, so example 4. Time for a weird one. Okay, follow along with this one. We got t plus 5 over radical t dt. Letters got to match from 1 to 9. Okay, so on this one, you want to do a rewrite step because it's not ready to do the integral yet, or the antiderivative. What might help you first is think of this guy as t to the 1/2. Okay, so if I have t to the first over t to the 1/2, and I subtract exponents, that piece becomes t to the 1/2. You're splitting it into this part and this part. Anytime you have a fraction with a single term on bottom, you have to do this move. If you don't, or if you had more than one thing on bottom, it's a type of integration that we don't do in this class. You won't even do it till Calculus 2 in college. The other one, there is no t's to cancel, and you have a t to the 1/2 in bottom, so it's really like t to the negative 1/2 here. So that was just a rewrite. I didn't take the integral yet. I didn't do any of my moves. Now it's time to do it. And you're going to raise the exponent up 1. So I'm going to put my brackets here from 1 to 9. You're going to raise the exponent up 1. Now be careful in that, because what's 1 bigger than 1/2? You're adding not 1 but 2/2. So you're going to get t to the 3/2, and then divided by 3/2 is ugly, so instead of dividing by a fraction, you can multiply by its reciprocal. So it's going to be t to the 3/2 times, flip it, 2/3. And then this guy, it was going to be 5t to the negative 1/2, but I want to make it go up by 1. Remember, that's 2/2. So now it's going to be 5t to the 1/2, and divide by the new exponent, you're going to multiply by 2 over 1. Now since there was already a 5 up there, it just multiplies by whatever else goes up top. So a cleaner version of this would be 2/3 t to the 3/2 and 10t to the 1/2. And then you're going to take a minute and plug in the 9 and plug in the 1, right? So, take your time, write it out. Oh, minus. Write it out. You're going to have 2/3 times 9 to the 3/2 plus 10 times 9 to the 1/2. Then you're going to do it again, 2/3 times 1 to the 3/2 plus 10 times 1 to the 1/2. You're going to plug that in, and I recommend getting an answer for these. Like this is 18 plus 30, if you type those in. And this will be 2/3, because 1 to any power is still 1, plus 10. And if you do that in your calculator, that could be one step, and you get 37.3 repeated. Still means the area under this curve. That's just a crazy curve to know the area under. All right, last problem. Okay, and our last problem is going to be pretty similar, just more fraction stuff. So we're going to go, because sometimes it just takes practice with those. If I had x to the 3rd minus 2 over radical x, right? First, I would recommend a rewrite. Okay, remember this is x to the 1/2. So if you take a half away from 3, think of this as like 6/2, right? Take a half away, it's x to the 5/2, because I'm splitting this up into 2 parts. Still have a minus sign between them. And then there is nothing with a 2, so it's 2x to the negative 1/2 dx. Okay, now it's ready for my integration part, 1 to 4. And I'm going to do this again. I'm going to go, we're going to go 5/2 and we'll bump it up by 1. Remember, 1 in this case is 2/2 more. So we're going to say x to the 7/2, and instead of dividing by 7/2, I'm going to multiply by the reciprocal. And then here, I would have had 2x to the positive 1/2, because I add 1 to that, divide by the new exponent, which means multiply by its reciprocal, and you get 2/7 x to the 7/2 minus 4x to the 1/2. Evaluated from 1 to 4. So if you type all that in, you can double check your answer. You get about 32.29. Okay, just make sure you can type these in well. Definitely use parentheses anywhere you see an x. Okay, so that should help you out with definite integration, which I like because you get number answers, and they mean areas. Don't forget that these all mean areas. All right, talk to you later, people.